Hey guys, welcome back. So now we're going to talk about the first derivative test. So I know we've been used to talking about derivatives, just some equations that we get after we apply all these rules on our function, but now we're going to talk about what the first derivative can actually tell us. And I'm not going to give it a big long introduction, we're just going to go ahead and dive right into it. So here we go. So the first derivative, right? There's a lot of stuff that the first derivative can tell us. Starting off with that the first derivative tells us when f of x increases and decreases. And what do I mean by that? Increases and decreases, right? And we're going to give it some arrows up and an arrow down for abbreviations, and you guys will see when I use those. But what do I mean by increasing and decreasing, right? So here I'm going to have that you guys see how from A to B my function is increasing, right? If you read from left to right, you can say that starting at this point and then you ending at this point, your function has increased, right? Which means that the y value has gotten bigger. Alright, now let's talk about when the function decreases, right? So let's talk about from B to C. You guys see how the function is decreasing, right? And we're actually going to use the first derivative to tell us all that. And how do we know when a function is increasing, right? The first part, increasing. So we know that the f of x is increasing whenever the first derivative is positive. So whenever the first derivative is positive, we're going to say that our function is increasing. And now, how do we know when the function is decreasing? We're going to know that when the first derivative is negative or less than 0, which is kind of easy to associate because positive means increasing, negative means decreasing. And why exactly is that? Think about that. So we have a first derivative that is positive. That just means that the slope, which is what a derivative is positive. And that means the slope to the line tangent at any point that we have here, right, is always going to be positive, right? Therefore, whenever our first derivative is positive, our function is increasing. Now here on this side that our derivative is negative, every slope to the line tangent is going to be negative, right? So we bring back the connection between slopes and derivatives with our graph, right? So pretty much whenever the first derivative is negative, our function is decreasing. Whenever the first derivative is positive, our function is increasing, right? So how do we know these breaking points where the function goes from increasing to decreasing? For example, what are we going to call this point B here, right? Which is the x value where the function stops. We're going to say that it stops increasing and then it starts decreasing. What are we going to call that value? And we're going to call those values critical numbers. We have it right here, right? That is a critical number. But how do we find these critical numbers, or what are they? All right? And critical numbers are the blank of the f prime. They're the blank of the first derivative. Critical numbers are the zeros of the first derivative. So in order to find this x value of b, we have to find the first derivative and we need to set it equal to 0. So we can solve for the zeros of the first derivative. Alright? And then let's talk about another critical number that we have here. We also have c. As you guys see, c is a critical number because our function here is going from, you guys see how it's decreasing from b to c. It is decreasing, and then after it reaches the bottom of c, it's going to go back up and it's going to start increasing again. So that is a critical number because our function changes our direction. That is critical point in our function, right? Now, if you guys see, b and c are different because when we have b, it goes from increasing to decreasing, which forms what we're going to say it's going to form a maximum value for our function. And here at c, it is going to go from decreasing to increasing, therefore it's going to form a minimum value, right? Because it's going to form a high point in our function and then a low point in our function. So we're going to call this right here a max, and we're going to call this right here a min. Now once again, how do we link these visual things back to our derivative? How are we going to say that, hey, this is a max, hey, this is a min, right? So we already know that we can find these x values, these critical numbers, b and c, by setting the first derivative to 0, right? But then after that, how do we tell that b is a max or that b is a min, right? How do we tell what these critical numbers exactly are? And we're going to have a maximum, which is going to be a change from increasing to decreasing, as you guys see here for letter B. For letter B, it goes from increasing to decreasing, which means that our derivative is going from positive to negative, right? So if we go from positive to negative, we're going to have a max. And we're going to see it like this. Going from positive to negative, we're going to have a nice little max there, right? From increasing to decreasing. And then we're going to have a minimum if we have a change from negative to positive, which means we're going to decrease and then we're going to go increase, and that bottom point right there, we're going to call it a minimum. All right? But where exactly do we see these changes from positive to negative? And that is going to be in the derivative. But when we do the example, our first example here in example 1, we're going to see how much easier it is to actually do all this stuff than it kind of sounds right now. Because right now it sounds like we're doing a lot of stuff. We're finding the first derivative, we're setting it equal to 0, and then we see where in these x values it goes from positive to negative, right? But now, let's go ahead and do an example so you guys can see that it's actually easier than it sounds. So here in example 1, we're given a function where I tell you that f of x is equal to 2x squared minus 8x plus 9. So this is some kind of quadratic function, some x squared function that we have, and we need to go ahead and answer these 3 parts about it, right? Using our first derivative test. So the first derivative is actually going to tell us a lot, and you guys will see. So the first part that I'm asking you in letter A is to find the critical numbers. And like I said in my second bullet, my critical numbers are going to come out from finding the first derivative and setting it equal to 0. So I'm going to go ahead and do just that. I'm going to find my first derivative, which is going to be 4x minus 8. And then I'm going to set it equal to 0. So I'm going to have f prime of x equal to 0. And I'm just going to write 4x minus 8 equal to 0. If I move over my 8, I get 4x equal to 8. And then if I divide both sides by 4, I get x equal to 2. So in this case, I just have one critical number, and I just found it, right? That is the first step. Just finding my critical number is going to be my first step. Then I need to tell you whether this critical number is a minimum, a maximum, or just neither. Because it doesn't have to be a change from positive to negative. Maybe this derivative is always positive. Maybe this derivative is always negative, right? But let's keep in mind that this is a parabola. So if we kind of think about how the graph looks, we should be expecting some kind of changes. And then we'll see how. So then, here in part B, I tell you to find the intervals when the function is increasing or decreasing. Cool. So, how am I going to do that, right? How am I going to see these 2 steps here that I tell you where the derivative is increasing or it's decreasing? And how we're going to do that is by telling you, I'm going to tell you, I need to look for where the derivative is positive and where the derivative is negative, right? That's what I told you. We can tell whether the function is increasing or decreasing depending on its derivative. And we're going to be using the number line method, which means that we're going to draw a number line. I'm going to draw a number line right here. Okay? I'm going to put my critical number on it. And then I'm going to pick a number below and above my critical number, an easy number like 0 for below, and another easy number like 3 for above my 2, which is my critical number, to plug them into my derivative. Therefore, I should always label my number line as y prime, or in this case as the number line of f prime of x, right? So since we're plugging in, or since we're going to have questions of where do we plug in these testing values in blue, and then we're always going to label our number line, and that is exactly where we're going to plug in these test values. So we're plugging in 0 into the f prime of x, right? Which is actually right here, right? Let's change up the colors. So we're plugging into 4x minus 8. So by plugging 0 into 4x minus 8, I'm going to get a negative number, I don't care what number I get. I don't care the fact that I get -8. I just care about the fact that I get a negative number and not a positive number. So let's go ahead and put that here, that I get a negative, I'm going to put that in red actually, I get a negative number if I plug in 0 into my derivative. Then if I plug in 3, which is my testing value, I can plug in 3, I can plug in 4, I can plug in 2.1 for all I care. But I'm going to plug in 3 because I feel like it's an easy number to test, that it's greater than 2. And if I plug in 3, I don't care about the actual number that I get. I just care if I'm going to get a positive or a negative. And I'm going to get a positive, right? So therefore, I know that the derivative is negative below 2 and the derivative is positive above 2. And what that tells me is that the function is decreasing before 2 and it is increasing above 2. So I'm going to go ahead and write that in my intervals. I'm going to have that increasing and decreasing. You guys see how I use my shortcuts. I don't write the whole increasing or decreasing. I just write increasing with an arrow up and decreasing with an arrow down. And I'm going to write those as my intervals of, you guys see it is decreasing anywhere in this area, anywhere below 2. So that's going to be from -infinity to 2, right? That is my interval that I'm decreasing. And where I'm increasing is where it's positive. Oh, actually I should put this backwards. Because I am decreasing here from -infinity to 2. And I am increasing for where the derivative is positive, which is here, from 2 to infinity. So my intervals where I'm increasing is here from 2 to infinity. So you guys see how my function changes from decreasing to increasing, right? So that's going to lead into the next part of this, which tells us to find the extreme values. And by extreme value, right, whenever I tell you an extreme value, it's just another way of asking you for my maximum and my minimum, right? But there's something very specific about this. Minimum and maximum, they're not asking me for the x value of my critical number. They're asking me for my value, my extreme value. And by value, I mean the y value. So let's write that somewhere here. I don't want the x value of my critical number. I want the y value, right? So first, let's talk about our critical number at x equal to 2. Here I have something that is going from decreasing to increasing, right? So what does that look like to me? If it's going from decreasing to increasing, it is looking like a minimum. All right? And we're going to call this a local minimum. So we say we're going to have a local minimum at x equal to 2. But that is not my answer, right? I want my value. So in order to find my value, I need to actually find the y value. And the only way to find the y value is by plugging in my critical number, my x critical number, into my original function here, which is f of x. So I'm going to go ahead and do that. And by doing that, I need to find f of 2. Alright? So if I plug into my f by doing all this hard work that we don't want to do, you guys can try this out on your own right now. Your answer is going to be 1. Alright? Your answer is going to be 1. Therefore, your local minimum is equal to 1. And you don't have a local maximum, or you don't have a maximum value due to the fact that your critical number was just a minimum because it went from negative to positive. So just quick recap before we run into another type of problem is that we need to first take the derivative. We take the derivative of our function, and then we go ahead and set it equal to 0, which we did over here. We set it equal to 0, and after we set it equal to 0, we get a critical number. It can be 1, it can be 2, it can be 100 critical numbers. After that, we draw a number line. And after we draw the number line, we check where we pick numbers, right, to check if the function is positive or negative in that interval. And that's going to be able to tell us if the function is increasing or decreasing in those certain intervals, right? And then we get to pick from changes from positive to negative or from negative to positive, where our maximums or our minimum are, right? And whenever I ask you for extreme values, I'm only caring about the y coordinate, not the x coordinate, all right? So let's go ahead and do another example in which we're asked a different type of question, but we still have to use the first derivative test. So let's go check it out. Okay? So for the first two parts, for the first part of A and for B, here in example 2, I'm actually asking you the same things. And you're probably going to be doing the same exact steps. So let's go ahead and do it. So in letter A, to find the critical numbers, I need to just find the first derivative and set it equal to 0. And yes, I see that you may be wondering, why do I have this interval here, right? You guys will find that in just a second. Just be a little patient here. So let's go ahead and do the first part, which is to find the critical numbers, which we do just, boom, let's just find a derivative. We are really good at doing that, especially when it comes to polynomials. We just get 3x squared minus 12x plus 2, well, that's 0. And after we take the derivative, we're going to set it equal to 0. So let's go ahead and do that. So we have 3x squared minus 12 equal to 0. And now to be a little nice, we're going to go ahead and solve for x by factoring out a 3x. And then we're going to get x minus 4, right? So then we set each of them equal to 0. So 3x equal to 0. And then x minus 4 equal to 0. This right here is just going to give me x equal to 0. And then this guy right here, the x minus 4 equal to 0, is going to give me x equal to 4, right? So then I have two values now. I have two critical values, two critical numbers that I'm going to be playing with. And what I mean here is that I'm ready to jump into the next step, which is part B, where I'm asking you to find the intervals when the function is increasing and decreasing, right? So in order to do that, we need to go ahead and draw out our number line. We need to go ahead and draw out the number line. Draw the number line. Let's make it a little bigger since we have two critical numbers now. Let's put 0 here and let's put 4 here. Doesn't matter that they're not equally spaced. Doesn't matter. And let's make sure we label it. Because now when we pick our values in between, we need to go ahead and make sure that we're always plugging into the derivative, because that's when the derivative is positive or negative. So let's go ahead and pick some values in between. So less than 0, a value just less than 0, I'm going to go with -1. Seems pretty easy. A value between 0 and 4, I'm going to go ahead with just 1. Those are easy numbers, they're easy low numbers, right? And then a value that is greater than 4, I'm going to go ahead with just 5. Right? So now you may think that we're done and we can go ahead and plug in some numbers. But actually, here's where that interval that we have up here, this interval here, comes into play, right? We need to actually use this interval. And it means that we don't care about the whole number line, how we did in the other problem. Now we're actually going to be restricted to this interval. We only care about the function increasing or decreasing within this interval. Okay? So let's go ahead and kind of like block it off, right? We're going to block it off here at -3. So I could have only chosen a number between 0 and -3, so I'm glad I chose -1. And then I can have to block it off here at 7 because it goes from -3 to 7. So I'm glad I chose number 5 because 5 falls between 4 and 7, right? So I'm good to go. I didn't make any crazy, I didn't choose any crazy numbers that were outside of my interval. So I'm restricted between my -3 and 7, which is my interval that I'm focusing on. I only care about what's happening in that interval, right? So now let's go ahead and plug in our numbers and see what we get, right? So if we plug in -1 into our derivative, here's a quick way of checking kind of what happens, right? So you can just plug in -1 into the whole thing, or you can use this quick way of checking, which I'm going to do in blue, right? So if I plug in -1 into 3x, right? If I plug in -1 here into 3x, what is that going to give me? that's going to give me a negative number. And now if I plug in negative 1 here into x minus 4, what is that going to give me? That's going to also give me a negative number. So now when I multiply, so actually let's go ahead and label this a little bit. Let's label this f prime of negative 1. So I'm going to get a negative number, I said, when I plug it into 3x, and I'm going to get another negative number when I plug it into x minus 4. So therefore I get a total of a positive number, right? So I'm going to go ahead and put a positive here. So I'm not even caring about the numbers that I get, I just care about the signs of what I get. So if I plug in 1 into my f prime, right, I'm going to go ahead and get, when I plug in 1 into 3x, which is the first part of my derivative, it's going to give me a positive, right? Remember that I'm just plugging into this part, and I'm plugging into this part, and then I'm multiplying their product to see what I get. I do find that easier than multiplying it into here, but if you find it easier to multiply into the actual long f prime of x, go ahead and do that. You're still going to get a positive number for when you plug in negative 1, and you're still going to get whatever I'm going to get now when I plug in 1. So now I plugged 1 into 3x, I got a positive. Now if I plug in 1 into here, which is 1 minus 4, that is going to give me a negative. So when I multiply a positive and a negative, I'm going to get a total of a negative number. So I'm going to go ahead and put a negative here. And now my last number that I chose was 5. So f prime at 5. When I plug in 5 into here, which is my first part, is going to give me, when I plug in 5 into 3x, is going to give me a positive. So I'm going to put a positive. And now when I plug in 5 here into x minus 4, it is also going to give me a positive. So I'm going to have another positive, and I'm just going to write it over here. So now that I see where my derivative is positive and negative, I can answer the question of whether where an f of x is increasing or decreasing. So I'm going to go ahead and start off with increasing, which is just arrow up, and it is going to be increasing wherever I see a positive, which is right here and right here, right? And that is between the interval, a closed interval, from negative 3 to 0. You guys see that I'm including my negative 3 because my negative 3 is blocked off like that. Alright, and then I'm stopping at 0. I'm not including 0 because at 0 it's neither positive or negative, it's just 0. Okay? So my interval is from negative 3 to 0. And also I need to include this last interval where I need to go from 4, not including 4, to 7, including 7, just blocking it off at 7. And then I need to go ahead and see when it's decreasing. I'm going to go ahead and see where it's decreasing. And I'm going to write the middle section here where the derivative is negative. That is going to go from 0 to 4. So here was a little different because we didn't have the crazy ends of infinity. We were just focusing on a smaller section of our function. We're just focusing on this part of our section, of our function. So now that we have computed part B, we're ready to go ahead and talk about finding the local max and finding the local mins, and then we can also throw in the absolute extreme values, right? And when I talk about an absolute extreme value, I'm going to tell you that we need to see what happens at the extremes. And by talking about the extremes, I just mean that I want to see what happens at my endpoints. So my extremes in this case of this function is going to be, the leftmost extreme is going to be negative 3, and the rightmost extreme is going to be 7, because those are the extremes of my function. So we got to take care about, when we do absolute max and mins, we got to care about the extreme values, and then we also care about the values in between, right? So real quick, we have that at 0, it goes from negative 1, at 0, you see how the critical number changes from positive to negative, right? So we're going to write that over here, right? At x equal to 0, our function goes from increasing to decreasing, which means it goes from positive to negative. Therefore, we have created a max, right? So we're going to say that at 0, we have a local max. And you guys see that so far we have just been finding local max and mins. We're going to see how the difference is to extreme extreme values, which extreme, I mean, we're talking about absolute max and min. So we're going to see the difference between local max and mins and absolute max and mins. So at 0, we just had a local max because it went from increasing to decreasing. And then we're going to see what's happening here at 4. So at x equal to 4, I'm going to have a local, I'll tell you now, we're going from decreasing to increasing. So I'm going from decreasing to increasing. That looks to me like a local min, right? It looks like a local min because here's what's happening in between the function, right? In between my extreme values. This is happening locally, which means in between the endpoints. But now to see which one is actually the absolute, we're looking for the highest value to find our absolute max. And our lowest value is going to be our absolute min. These are just local, right? And I'll show you guys in a quick picture up here what the difference is, right? So let's say we have like a function, right? The function can look something like this, right? Right? There we go. We got a good function right there, right? So let's say that I have here a local maximum and I have a local minimum here, right? I have a local minimum there and I have a local maximum there. That doesn't mean that those are my highest points, and that doesn't mean that's my lowest point, right? Because all those two are my local max and min. I can have an absolute min, which is going to be right here because that is my lowest point, and then I can have an absolute max because this right here is my highest point. I have my lowest point, so this right here we're going to say that it's absolute, and then this right here is going to be absolute, while this right here is local, and this right here is local. Alright? So we went ahead and just talked about local and absolute all at once. So how are we actually going to compare, how are we actually going to see if at x equal to 0 I have a local max, or is it an absolute max? How do I know between the two? So what we're going to do is we're actually going to just do a x and f of x chart, right? In which the first and last, well, I only need 4 boxes, and you guys will see why. I only need 4 boxes. And the first and last are going to be my endpoints, right? So my endpoints are -3 and 7. And then in between, I'm going to put my critical values, 0 and 4. So here I am putting my critical values, my critical numbers, and then outside here I'm putting my endpoints, which is given by my interval, right? And now we're gonna go ahead and plug in -3 into my f of x. So if you guys do that, if you guys plug in -3 here into my f of x, into my function, you guys will see that you guys get -79. Okay? If we plug in 0, we get 2. This is all if you guys do it on your own, right? If you guys are plugging in 0 into the original function, you guys will get 2. If you guys plug in 4, you guys get -30. And then if you guys plug in 7 into your f of x, you guys get 51. So now if we see here, what we can see is that the lowest value actually occurs, right? So the lowest value actually occurs here at -79, right? So our absolute minimum occurs at x equal to 3 with a value of -79. So we have an absolute max, an absolute min of -79 at x equal to 3. That's exactly what we get from our chart. Then we have an absolute max, right? Our highest point, which is our absolute max, is going to be here of 51 at x equal at x equal to 7. Right? And then we can say that we have a local max. We have a local max of 2. We have a local max here of 2 at x equal to 0. So 0, we still have a local max at x equal to 0, but it's a local max of 2. And then here at x equal to 4, we have a local max of negative 30. I mean a local min of negative 30. So these values are not wrong, right? We still have a local max and a local min, but that doesn't mean that they're the absolute max and they're absolute min. And in order to check whether the absolute max or the absolute min, we need to go ahead and draw our chart where we talk about our critical numbers and we talk about our endpoints, and then we discuss the highest of all. That's going to be our absolute max, and then the lowest of all is going to be our absolute min. And that's kind of the idea that I drew out here, right? Here I have a local max, and I have a local max, and I have a local min, but I also have an absolute min and an absolute max. And that's the idea that we have here. But don't worry, we're going to go ahead and do more examples on this stuff, so make sure we just get it down packed. So let's go ahead and do some practice problems.